At the dawn of the 20th century, a young physicist named Albert Einstein forever changed our understanding of the cosmos. His theory of relativity, presented in two parts, Special and General Relativity, shattered the Newtonian view of a static and absolute universe. Einstein revealed a universe where time and space are intertwined. Gravity is not a force but a curvature of this space-time fabric, and energy and mass are two sides of the same coin. Einstein's revolutionary ideas were not just theoretical musings. They had profound implications for our understanding of the universe, from the smallest particles to the largest galaxies. His theories predicted phenomena like black holes and gravitational waves, which were later confirmed by observations. Relativity became a cornerstone of modern physics, essential for understanding the workings of the cosmos and our place within it. Published in 1905, Einstein's special theory of relativity challenged the established laws of motion. It was built on two fundamental postulates that revolutionized our understanding of space and time. The first postulate states that the laws of physics are the same for all observers in uniform motion. Imagine you are on a train moving at a constant speed. If you throw a ball straight up in the air, it will fall back into your hand. To you, the ball's motion appears simple. Now, imagine someone standing on the platform observing the same event. They see the ball moving horizontally with the train's speed as it travels up and down. Despite the different perspectives, both observers agree on the laws of physics governing the ball's motion. The speed of light, a cosmic speed limit. The second postulate is more radical. The speed of light in a vacuum is constant for all observers, regardless of their relative motion. This seems counterintuitive. If you shine a flashlight while on a moving train, you might expect the light to travel at the speed of light plus the train's speed. However, Einstein stated that light always travels at the same speed, approximately 299,792,458 meters per second. These two seemingly simple postulates have mind-bending consequences, leading to concepts like time dilation and length contraction. Time dilation. Time is not absolute. One of the most startling consequences of special relativity is time dilation. It states that time is not absolute but is relative to the observer's frame of reference. Time slows down for objects in motion relative to a stationary observer. Imagine a clock traveling at incredibly high speeds. According to special relativity, time would pass slower for that clock compared to a clock at rest. This effect, known as time dilation, becomes more pronounced as the speed of the moving clock approaches the speed of light. While the time difference is negligible at everyday speeds, it becomes significant at speeds approaching the speed of light. This phenomenon has been experimentally verified using atomic clocks flown on high-speed jets. The clocks on the jets showed a slight but measurable time lag compared to synchronized clocks on the ground. Length contraction, shrinking objects at high speeds. Another bizarre consequence of special relativity is length contraction. This concept states that the length of an object moving at a high speed appears shorter in the direction of motion to a stationary observer. Imagine a spaceship traveling at a significant fraction of the speed of light. To an observer on Earth, the spaceship would appear shorter in length compared to its length when at rest. This contraction occurs only in the direction of motion. Like time dilation, length contraction becomes more pronounced as the speed of the moving object approaches the speed of light. However, it's important to note that these effects are only noticeable at incredibly high speeds, far beyond what we experience in our daily lives. ALMC2, unlocking the power within matter. Perhaps the most famous equation in physics, ETLMC2, also arose from special relativity. This elegant equation describes the relationship between energy and mass, stating that they are interchangeable. The C2 represents the speed of light squared, an enormous number signifying the vast amount of energy stored within matter. This equation revealed that even a tiny amount of mass contains an immense amount of energy. It explained the energy released in nuclear reactions, like those powering the sun and nuclear weapons. It also laid the foundation for understanding the early universe, where energy condensed to form matter. The implications of ETLMC2 are profound. It demonstrated that matter itself is a form of energy, blurring the lines between these fundamental concepts. This equation revolutionized our understanding of the universe's building blocks and paved the way for new technologies.